Okay, so let me go over this again. This is second take. Okay, we're talking about solutions right here, right? So even though matter is categorized mainly into pure materials and mixtures, my focus will be on the mixture component, okay? So in looking at mixtures, we do have two main types, and that's the homogeneous mixture and the heterogeneous mixture. Once again, my focus is the homogeneous mixture because the homogeneous mixture makes up a solution. Now we're caught up, okay? So looking at the solution right here, let me give you guys a little background. But before I get into that, let's hop over here to the right where we're seeing different examples of homogeneous mixture. The key factor in the homogeneous mixture is the mixture looks uniform. Here we have a cup of coffee. Coffee sounds good right about now, but it's late in the day, 6:30, 7 p.m. I do not need coffee, right? But coffee, once you mix it up with cream and sugar, when you stir it up real good, it does look uniform in appearance, even though you have a mixture of coffee, water, creamer, and sugar, right? But when you stir it up real good, it looks uniform in appearance, unless you add something that makes it look ununiform, right? Over here, wine, once again, is a mixture of a lot of different chemicals in the wine solution. But we know it's a mixture, but it's homogeneous because it appears uniform. Air, even though we cannot really see the components of air with our naked eyes, we recognize it's a mixture of gases based on experience. Brass is one example where we have a mixture of different metals, zinc and copper to be precise, to make brass. We also have steel, natural gas, vinegar, and blood. All of these are examples of different mixtures. So what I want to do right here is to scroll down so I can discuss mixtures in more detail. So let's see, how do I clear the drawings? Clear all my drawings. Oh, great. Okay, so back to this. In talking about the mixture, right? And in talking about the solution, overall, you can have two main types of solutions. So we understand that to make a solution, you have to mix at least two components, two main components. You have the solute mixed with the solvent, plus the solvent, and together they make the solution, okay? Together we get the solution. So in general, we are told that the solute component is defined as solute because it's the lesser amount. And this is all relative, right? So compared to everything else, it's the lesser amount, or it's less. So it's a solute. The solvent tends to be the greater amount. Once again, this is all relevant, right? Sorry, relative, right? So comparing the two, the lesser amount is solute, the greater amount, or is a solvent. And when you mix these up to get a uniform mixture, this is called the solution. The solution, once again, is that uniform or homogeneous mixture, okay? So this right here is the mixture. Okay, so what kind of things can you mix to form a solution? Well, in general, we're looking at polar, right? You either have a polar solution or you don't. So if you're gonna have a polar solution, then both the solute and the solvent have to be polar. So here we have examples such as, I won't give specific example, but in general, if you have a polar solute and a polar solvent, this will actually yield a polar solution, okay? And so it's important that the nature of intermolecular forces, of the nature of the type of bonding in the molecule matches. When you have that rule of like dissolves like, the like they're referring to is the bonds that we see within the molecule. They have to be similar in some ways, okay? So go back to review the rules about polarity, and you wanna look at that. Remember polarity, I'm trying not to reteach that whole section here, but it's about the differences in electronegativity, okay? So if I were to draw the molecule as a circle right here in general, remember, if you have a polar molecule, you have a polar molecule because the charges, the electrons and the positive charge within the molecule are polarized, right? They're separated from each other. So within the whole molecule, one side of the polar molecule is mainly positive, the other side is mainly negative. So when you have these distinct charges in the molecule, it's easy for them to attract or to dissolve something else that has a similar property, right? Remember, in the polar molecule, you have what they call permanent dipole. That just means dipole means two, right? And you have two main charges that are very distinct, and they mainly exist on opposite ends of the molecule. Okay, so I'm trying to give you guys a short version of this, not going into a lot of details, but that's the bottom line. So if you have one polar molecule dissolving another polar molecule, you can see why, right? The negative end attracts the positive end here, and then the negative end attracts the positive end here, and together they're able to form the solution, okay? We actually see that we're seeing right here that an ionic solute will dissolve in the polar solvent. How does that help? Okay, so let's look at ionic. Ionic compounds are technically compounds that contain positive ions attached to negative ions, okay? So do you see what's in common here? If a positive ion is attached to a negative ion and it's put in a polar solvent, you can see here the polar solvent has got a component in the molecule that's positive and a component in the molecule that's negative. It's technically, actually, to be technical, it's partial positive and partial negative. I'm trying not to complicate this, but yeah. Ionic compounds are the ones that have fully positive and fully negative. Polar compounds have partial positive, partial negative, okay? Once again, try not to overwhelm you guys with the details, but yeah. So when you have this going on here, what we see is, even if it's partial, it's still positive. So the positive here is drawn to the negative on the ionic compound. Then the partial negative here is drawn to the positive on the ionic compound. So whether you have ionic compound, this is ionic, that's a solute, or you have a polar compound, that's a solute, these will both dissolve in a polar solvent because of similar forces, okay? In this case, you have the same force, right? In this case, we have similar forces. Similar, okay? Once again, to be clear, when you have a polar molecule, the reality here is in polar molecule, the charges are partial positive and partial negative, which this was talked about before, right? So these are same, and over here, these are similar, but it's similar enough to dissolve it, and that's the bottom line. So of course, in the rule, which is the last question, you'd be asked, what is the general rule that governs the formation of solution? And you're saying like dissolves like. As long as the forces are similar, as long as the bonds are similar, the molecules will form a solution. So if you have a polar solute and a polar solvent, they will form a solution. If you have ionic solute and a polar solvent, they'll form a solution. Why? The forces are either same or similar. So let's go down to the actual lab and see what's going on here. You're given a data table that shows you various possible kinds of solutions. So I went ahead and did some research so I can get it right this time, okay? So I'm gonna give you some examples. Remember, solute is the lesser component. This is the lesser. And then solvent, this is the greater. So this is greater in amount. Oh, the one thing I forgot to mention, which I should before I continue right here, you will notice that the solute and the solvent can have different physical states, right? According to this table right here. Can be liquid, solid, whatever. But let me use an example that we're very familiar with, which is a solute that is salt, okay? A salt, of course, would be a solid, and a solvent that is water. So we understand how to make salt water, correct? The water is going to be liquid. If you take salt, a small amount of salt, to make sure salt is a solute, and dissolve this in water, we get a solution that we call salt water. Salt water will be a liquid. And so we tend to know in general that the salt water takes the physical state of the solvent. Why? Think about it. Why does the physical state match the solvent more than it does the solute? If you think about it, you probably guessed it right. It's because you have more solvent than solute. There is greater molecules of solvent. You just said greater molecule, greater amount than you have solute, right? So the solution tends to look more like the solvent because there's more solvent. There's greater representation of the solvent molecules. Okay, Now let's go over here and look at the example we have here. Okay, so to annotate this, let me go ahead and click on here, annotate. Okay, so looking at different examples, I had to change my table so it matches the table here. So I'm saying this correctly. Remember, in the forming of the solution takes the physical state of the solvent because the solvent is a greater component, right? So I'm going to give you various examples of these solutions right here. I try to make sure I got one for each combination. When you have a solid and solid example or solid and solid mixture or solution, the example of that is going to be brass. Okay. And then when you have a liquid inside a solid, the example that we have for that is Jello. Okay. Jello is the consistency of liquid inside a solid. And then gas inside the solid, the example of that is ice cream. And you can even think maybe styrofoam or marshmallows, kind of that texture, right? And then over here, we have a solid inside a liquid. That will be what? Salt water. Salt water. Excuse my handwriting. I'm writing with the mouse. And then liquid and liquid, that can be vinegar or alcohol. So I'm going to use vinegar here. Vinegar. That's a more common example that we know of. And then a gas inside a liquid mixture, example of that will be soda, right? We can relate to that, soda. And then the solid inside a gas, the example for that will be smoke. You know, the smoke particles inside air, smoke. Liquid inside the gas, example for that will be hairspray. So hair spray. When you have those fine particles, right? And then gas and gas mixture, the example here is air. So from this table, we are made aware of all these mixtures and solutions around us that we may not have really noticed that are formed by a different solute and solvent combination. Now remember, for a solute and solvent to come together and form a solution, we need to have similarities in polarities, right? Okay, let me clear my drawings and scroll down. Okay, so they tell you here the different intermolecular forces. They're talking about the van der Waals. So you're giving a little bit of a background. So I'll give you guys a brief background and not go over it. The van der Waals attractions, these are attractions that are temporary dipoles. It says here, these are formed due to the attractions between temporary dipoles induced in neighboring molecules by momentary asymmetries in the electron cloud distributions. And these are present in all materials. Okay, van der Waals forces are present in all materials. So to try to keep this simple, I'm going to use it, look at molecular compounds versus ionic compounds, right? So a compound like, let's say carbon dioxide. Carbon dioxide is nonpolar. And when it's nonpolar, it has what they call these temporary dipoles, okay? So I don't want to skip over all of this before we go into the solution because this does determine what kind of solution we'll have. So we'll see here that now this is saying here that this type of intermolecular force, van der Waals, exists in all kinds of molecules. If you have a nonpolar compound like carbon dioxide, nonpolar has van der Waals. I'm going to just write the acronym here, VDW only, okay? So nonpolar molecules tend to have this van der Waals forces only. So let me try to use that picture I used earlier to illustrate this point here. So because we're saying here that CO2 is nonpolar, CO2 in general doesn't have a distinct area where the electrons are versus a distinct area where the positive charges are, where the negative charges and positive charges are. But sometimes for a small moment, we have a momentary asymmetry. So instead of having the negative charges dispersed evenly throughout the molecule, sometimes for a fraction, it feels like a fraction of a second, for a moment, you have the electrons all in one. I didn't mean to do that. Let me undo. Okay, you have the electrons all stationed or focused or accumulated in one corner of the molecule. When the electrons are in one corner of the molecule, by default, the opposite corner of the molecule is positively charged. Okay? So even though in general, nonpolar molecules tend to have even distribution of electrons and easy distribution of positive charges, making them nonpolar because they don't have the positive charges on one corner of the molecule kind of segregated. You know what this reminds me of? I want to say middle school dances. In middle school dances, before we got comfortable with the guys, the girls would be standing in one corner of the room, the guys would be standing in one corner of the room, and then everybody's afraid to ask the other person to dance. The girls are waiting to be asked. We're all standing there all shy and kind of smiling and stuff. Then after a while, you know, things get comfortable, people get comfortable, and they kind of come to ask each other to dance, and it looks more like this, right? So before they ask each other to dance, after, then we're all mingling and everything looks all uniform. Anyway, when you have the charges in the molecule separated, this is called polarizing. The bottom line here is, for a moment, the molecule that was nonpolar, this is more like a nonpolar, becomes polar. Okay? It's a momentary thing, polar. And so this is called a temporary dipole. So for a temporary moment, the negative charge remains separate from the positive charge. And when this happens, the molecule that behaves this way influences or induces the neighboring molecule to do the same thing. Before you know it, the whole solution. So you know how they say you can be influenced by your neighbors or your friends? That happens here. It started off nonpolar. For a moment, we have a temporary, I can't spell temporary or even right. We have a temporary dipole, so it's temporarily polar, but this happens here and influences the neighboring molecule. Now we have the negative charge over here, positive over here. Before you know it, the whole molecule has this temporal dipole situation. This is what causes van der Waals forces, okay? So nonpolar molecules have van der Waals forces. So I mentioned this earlier, that in order to have a solution, if you're starting off with the nonpolar carbon dioxide, you need to add it to something else that's nonpolar, okay? So this is nonpolar. I'll just say NP for short. You need to add it to something else that's NP to get an overall NP solution, nonpolar solution, okay? So I'm giving you the bottom line. CO2, it can't be water. It has to be something else, maybe like methane, something like that, okay? Something that's nonpolar. And when you add these two, you get a nonpolar solution. Okay, so dipole forces, these are forces that are seen in molecules with what they call permanent dipole. So to illustrate this part here, let me clear all of this, clear all my drawings, back to this here. Solutions that have a permanent dipole, these are solutions that are technically dipole all the time. They're not switching on and off. They're dipole all the time. No matter where you see them, they are always dipole. Example of that is water. Water is dipole all the time. Water is made up of H2O, right? So I'm going to draw the water molecule real quick right here. This is the water molecule right here. So remember, it has lone pairs over here. That's what makes it have that V shape or the bent shape. This water molecule is polar. What makes it polar? Well, we mentioned this before. You can look at the lone pair in the central atom. If water was linear, water would not be polar. But because you have these unmatched surrounding groups and unmatched electron groups around water, water has quote unquote an undissolved dipole. So let me try to translate this water here into one of those blob pictures, right? Oxygen is electronegative, so it gets a partial negative symbol. This is the symbol we assign electronegative atoms. Hydrogen is relatively less electronegative, so we assign this the partial positive symbol. So as a whole, to simplify this structure, I can draw this into a blob and make the oxygen side more negative and then the hydrogen side more positive. Okay, all I've illustrated here overall, there is one side of the molecule that's relatively more negative, the side that has the oxygen, the other side that has the hydrogen is more positive. And this is water, so it always has that configuration. One side is more negative, the other side is more positive. So they call this a permanent dipole. Remember, dipole refers to having two opposite charges, in this case, two opposite poles, okay? So if you have water that is polar and has a dipole, and you want to make a solution, you have to add it to something else that is polar, and polar and polar, polar solute and polar solvent will make a polar solution. Okay. So hopefully you get that. Polar, polar make polar solution. Polar solute, polar solvent make polar solution. So the first one we saw was nonpolar, nonpolar make a polar solution. Remember, if a molecule is polar, it tends to have a dipole force. I'm trying to give you guys, to do the lab, you really don't even have to understand things at that deeper level. But since you asked me to do the video, I'm doing the video at that level. Yeah. Okay. So the last level we're going to be looking at, let me clear all of this. Feel free to rewind if you want to watch this over again, is I'm going to be looking at the ion dipole. So even though we said light dissolves light, surprisingly, but not really surprisingly, an ion can dissolve in a dipole solvent. So what happens here? We just defined what a dipole looked like, right? So let me go back to drawing a dipole. This is going to be my water blob. So one side of my water blob is negative, the other side is positive. This is where we have our oxygen side, and here we have our hydrogen side. So how is it possible that this dipole molecule, right? The molecule that is polar, that has the dipole intermolecular force. How is it possible that this molecule here can dissolve something that's ionic? So the example for dipole, remember, is water. The ionic here, it will be like table salt. So let's say sodium chloride, table salt. Let me show you the picture I'll represent for the ionic compound. Remember, ionic compounds are made of not two ions, but in this case, two ions, right? Sodium is positive and chlorine is negative. So you see the theme here, right? In the dipole or the polar molecule, you have a permanent dipole. In the ionic compound is sometimes called the extreme dipole. Why? Because the positive and negative side in the molecule was so extreme, they quote unquote broke up, but they're forced to stay together because of the opposite charges attracting, right? So here you're seeing opposite charges attracting, right? But you can see how the negative charge is very separate from the positive charge. So when these are trying to attract each other, the positive end here draws in the negative end here. And then, of course, the negative end here draws in the positive end here. And this is how the solution is formed. So the solution is formed by what we call the ion dipole interaction. Okay, so now we have an ion dipole interaction formed by when the ion is attracted to the dipole. And you can see why they're attracted, right? Opposite charges. So I won't go into any more of this. We're told in here, in particular, the greater the similarity between the solute and the solvent, the higher the solubility, like dissolves like. Okay, so these here, the intermolecular forces here aren't exactly alike, but they're very similar, right? So we can see here, ion dipole is more of a similarity thing. Okay, so let's go ahead and scroll down and move into the actual instructions. So here, like we saw before, you have your solute, you have your solvent. The differences here have nothing to do with the physical state. The differences here has to do with polarity. So I just explained here that salt is an ion. So you can see right here, the salt will be an ion. The categories we have here are either ion or ionic or polar or non-polar. So all of these chemicals here fit into one of these categories. So you get to decide which one it fits into, okay? So what I'm going to do right now to help you guys out with this is the lighter fluid here is going to be non-polar. I'll help you guys with that part. But you have to figure out the rest of these, okay? What category do they fall in? And of course, when you go ahead and figure them out, I'm going to work the first one for you. Of course, salt and water form a solution. So water here is polar, right? Salt is ion. So we know it will form an ion dipole interaction. These will form a solution. So how do they want us to write this down? Let me scroll down here. Did they give us an example? I think they said S. Oh, this is SS. You can just say solution. Oops, this is right here, right? Yeah. You can say solution or check yes for solution, whatever, whichever, I mean, works. So you can say yes for solution. Why won't this let me draw? You can click yes for solution, or you can write the word solution. Solution. I think I like the word better than the check mark. It's a lot more meaningful than just checking it. Okay, so solution. Oops. This is a struggle just to write. How do I get rid of this? Clear. Oh, well. Let me see. How do I get rid of this? I can't. Okay, it's right here, solution. Okay. So then I scroll down here with my mouse. Let me clear all drawings right now, because at this rate, that's kind of annoying. Okay, so my first one, when I'm filling this out, oh, right here. Now I see the problem right here. My combination is solute and solvent. So my solute was salt. My solvent was water. And then it says the solute is what? Now remember the options were ionic, polar, and then non-polar. Oh, excuse my handwriting, polar. It's supposed to be R, I just dragged it a little bit. Okay, so I am polar, non-polar, but here they break it down to two, just polar and non-polar. So if anything is ion, just label it as polar, okay? So salt will be labeled as polar, and then for it's our solute, right? Our solvent is water, that will also be polar. So of course, if it's polar and polar, we expect to have a solution. So solution, yes. Then go through. Okay, if it's a solution, if it's not a solution, check it over here. And then when you're done filling the whole table, to look at these patterns in the table and draw a conclusion about the different combinations. So you don't want to write like every solution. What's the general observation? Because you only have this small spot here to fill. What can you say in general about the chemicals that form a solution? I think I scrolled out of. I'm going to stop the recording. I am done with this lab.